Today's lesson is 2.4, identifying functions. So we're now transitioning into looking at specific types of relations. We looked at x relationship to y, we looked at domains relationship to range, we looked at the independent variable's relationship to the dependent variable, and now we're looking at a special type of relationship called a function. So the goal today is to determine if a relation is a function. So we're going to look at several different relations and figure out whether or not they meet the criteria for a function. So let's figure out what the criteria of a function is. And that is in fact our main key term here today is function. You've seen some of these other terms, we've defined them already, but the term we're going to define today is function, because we need to know what the criteria of a function is if we're going to be able to identify it. So you can see this diagram right here. We've got some input that goes into the function and then produces some output. Now this function box is normally represented by some expression, and the input is some value and the output is some value, and in the end you express that relationship with the input to the output as an ordered pair. So this is kind of a diagram definition, but the more formal definition of what a function is can be expressed as a special relationship, is very special, where one input is paired with exactly one output. So real quick, what this looks like would be if we have some x. It always happens. One time a video that will come up. That's the last one today. X is paired with y. So let's say x is some value and it's paired with this y value. That is a function because this x value is paired to one y value. This is a example of a function, right? More conceptual example, of course. Now what if we had this x value paired to this y value and to this y value? Two different y values. Well, the definition of a function says that an input is paired to exactly one. Exactly one. That's the important part of this definition. Exactly one output. So the first example is definitely a function because the x is paired to one y. The second example is not an example of a function because the x is paired to two y's. And I'll give you a third example, and this is the difference between this is where a lot of students get confused. So let's say we have two x's paired to the same y. Well, if you think about the definition of a function, each input is paired to exactly one output. It doesn't say that two different inputs cannot be paired to the same output. It doesn't say that anywhere. So in this third example, it is also a definition of a function because this x is paired to only one y, and this x is paired to only one y, and it just happens to be the same y. So function, not a function, function. So let's quickly define what function notation looks like. So function notation is a important part of a function because let's say if y equals 2x plus 1 is a function, we've figured out that it meets the criteria of a function, then it can be written as, and because it's a function, it can be written as f of x equals 2x plus 1. So essentially what happens here is if your equation is in fact a function, you can replace y with f of x, so function of x. That's the main difference between this equation right here and this equation right here is we've determined that y equals 2x plus 1 is a function, so we've taken out y and we've replaced it with f of x. So we can actually say that y equals f of x. When you see f of x, it's the same thing as seeing y, but you know that we've declared it as a function because each input is paired to exactly one output. So let's look at some examples today, what functions look like. The first example is a table. So we've got two tables. One of these is a function, one of them is not a function. As I go through this example, hopefully you're trying to figure out, okay, is the right one a function? Is the left one a function? So here we have x, y, and we've got 9 paired to negative 9, we've got 15 paired to 6, we've got 14 paired to 12, and we've got 8 paired to 7. So I don't see any repeating x values. 9's only paired to negative 9, and it looks like all other x values are paired to only one y value. So we've got 15 to here, 9 to here, 14 to here, 8 to here, and all of our x's are paired to one y value. So this meets the definition of a function. This is a function right here. What about the example to the right? We've got 5 paired to 2, we've got 4 paired to negative 7, we've got 2 paired to 8, and we've got 5 paired to 3. Now this is an example of a non-function, and the reason why it is because we've got 5, which is paired to 2, the input is paired to the output of 2, and the input of 5 again is paired to the output of 3. So if this were a function, then our input 5 should only have one y value or one output. And in this example, it's got 2. It's got 2 and it's got 3. So this is an example of a non-function. So we've got a function right here, and we've got a non-function. That's what it looks like in a table. Let's look at what it looks like when we're given a map. So here's our map. We've got our domain mapped to our ranges, right? So which one of these is a function? Which one of them is not a function? So let's look at the first one on the left. If you look at the domain, we've got 3 domain, 3 x's, and it looks like this negative 6 is paired to only 8, this 7 is paired to only 2, and this negative 2 is paired to only 8. Now, it's okay if an input is paired to the same output as another input, as long as that input is paired to only one output. And you see that the arrows for each of these inputs, there's only one arrow for each of the inputs. So that's a strong indication that this is a function, and it in fact is a function. So we can go ahead and say this is a function, and it happened again. And then if you look at the right example, we've got 9 paired to 2, 19 paired to 2, which is okay. We've got negative 6 paired to negative 10, and we've got negative 6 paired to 16. So again, if you think about what the definition of a function is, one input to exactly one output, this negative 6 is paired to 2 different outputs. It's paired to negative 10, and it's paired to 16. This is an example of a non-function. And now, what does it look like in coordinate points? And coordinate points very similar to tables in maps. So we've got negative 3 is paired to negative 3 is paired to 5. We've got 5 is paired to negative 3, which is okay. We've got 8 paired to negative 3. So we've got an input paired to negative 3. We've got another input paired to negative 3, but so far we've got no repeating inputs paired to a different output. And we've got negative 3 paired to 5. So this is just a repeat of the first coordinate point, and that's okay. Negative 3 is paired to 5, negative 3 is paired to 5, so this input of negative 3 is paired to the same exact output in both of the examples. So this meets the definition of a function because we've got negative 3 is paired to 5. That takes care of these two. We've got 8, which was paired to negative 3. And we've got 5, which was paired to negative 3. So you can see that there's only one arrow for our input pointed at an output, and that's an indication that this is a function. So we can say this is a function. Now this example over here to the right, look at the input values, look at the output value. So we've got the input value of 5 paired to the output value of 2. We've got the output or input value of 2 paired to the output value of 6. We've got 4 paired to negative 1. And we've got 2. And I'm going to go ahead and erase this 2 because 2's already been written. We've got the input value 2, which is paired to the output of negative 2. So you can see in this example that this input of 2 has two different outputs. It's pointing to two different y values. It's pointing to 6. It's paired with negative 2. You cannot have an input that is paired to two different outputs. So this is an example of a non-function. And our last example today, and this is more of a conceptual or real-life example, so I want you to think and think about our definition of a function. An input paired to exactly one output. So we have the pairing of a cell phone number to a phone. If this meets the definition of a function, then each cell phone number should be paired to one phone. You can't have a cell phone number that's paired to multiple phones. So when you dial your mom's number, does it always go to the same phone? When you dial somebody else's number, does it always go to that other person's phone that you're dialing? It does. Every phone number causes the same phone to ring. So each number is paired to one phone. This is an example of a function. Now look at the second example. The pairing of a zip code to a home. So we've got zip codes to homes. So for example, A5340 is the zip code of Litchfield Park. And when I lived in Litchfield Park, next to the Wigwam, that was my zip code. It was paired to my house. That is a terrible house. It's like a Spanish-built home. Well, I moved recently to another house that was outside of Litchfield, not by the Wigwam, but my zip code remained the same. It was still A5340. So it was paired to my childhood home, and now it's paired to my adulthood home. So is this input paired to exactly one output? No, it's not. It's paired to multiple outputs. So the pairing of a zip code to a home is not an example of a function. Now if you flip this and you say the pairing of a home to a zip code, right? So if we've got my childhood home, or my adulthood home and my childhood home, right? And we say the pairing of a home to a zip code, would this be an example of a function? Absolutely, because this home is paired to this zip code. It does not have another zip code, so it's only paired to one zip code. So this would be an example of a function if you flipped it. If you have any questions or concerns, please message your classmates in Schoology and they will do their best to help you out. Good luck on the problem set.